Hi guys, and welcome back to Introduction to Mechanical and Automotive Engineering. I'm your lecturer, Dr. Elizabeth Kyriakou, and today we're going to continue with our lectures on structural analysis, and we're going to take a look at zero force members. So, what is a zero force member? It's a member that the force equals zero. So F equals zero, which means the member has neither tension or compression. So why do we have zero force members in trusses? So this is purely to provide stiffness to the structure and stability. So there are a few rules which we can use to identify which members in the truss are actually zero force members. So let's identify some zero force members. Okay, so we actually have three rules. And the first rule is rule 1. If I just draw a point here and I have a force on this side and a force on this side, so here I have to say I have F1 and F2. For this system to be in equilibrium, F1 has to equal F2 for equilibrium to occur. So let's just take a closer look at that. So at the moment we've just put forces and we haven't put any directions on it. So if I take a look at this question again, and here's my joint, and now I'm going to put a force on either side, the direction, and let's just rotate the x-axis to make it, the y-axis to make it simpler. If I take some of the forces and use my equations for equilibrium, let's just write them up here. Some of the forces in the x direction has to equal 0, some of the forces in the y direction has to equal 0, and some of the moments around a point also has to equal 0. So if this is my axis, I can resolve the forces in the x and the y direction. So here we only have forces in the x direction. So if I say some of the forces in the x direction has to equal 0, I'm going to have one that's going to be positive F1 and F2 is going to be negative. So therefore F1 has to equal F2. So then I'm going to be in equilibrium. Okay, so that works out for me. So F1 has to equal F2. If I redraw that and I say that instead of the members being in tension and now that they're in compression, so they're going towards the joint, and here I have F1 and F2, I can do my equation for equilibrium again, and here I have some of the forces in the x direction equals 0, and I'm going to have F2 minus F1, and again F1 has to equal F2 for me to be in equilibrium. So here I'm in equilibrium. So we should be able to identify that the forces, if they're going away or towards each other, so if they're both in compression or if they're both in tension, that the resultant is going to be F1 will equal F2. What happens if this is not the case? So if down here I redraw and I have F1 and F2 going in the same direction, am I still going to be in equilibrium? So let's just take a look. sum of the forces in the x direction has to equal 0. So here I'm going to have F2 plus F1. So that means my whole system is not going to be in equilibrium because I'm adding up these two forces. That means the whole system is moving this way. So it's actually going to move. So here we're going to have, it's not in equilibrium. Okay? And this is going to be the same if we're going in the other direction. So that's rule 1. Let's take a look at the second rule. So let's just clean this up. Alright, so now if we take a look at rule 2, what do we have? If we have a member, so we have two members and we have another member going this way, so I can have A, B and C. Let's have a look. So if here is my X and Y direction. So, for this member, this scenario to be in equilibrium, to remain in equilibrium, member A and B must be equal. And what happens to member C? Member C is going to equal 0. So that's going to be our zero force member. And let's go and have a look why that is. Okay, so if here I redraw that diagram, and here I have, this is A, C and B. So it shouldn't matter what this angle theta is. I'm just going to assume that all my forces are in tension. So here I'm going to have FA, FB, and here I'll have FC. And again, I'll put my axes this way. So if this was perpendicular, then straight away I would know that FC was a zero force member, but it's not at perpendicular. So let's take a closer look. I know that if I do some of the forces in the x direction, I have minus FB plus FA, therefore FA has to equal FB, okay, for equilibrium to occur, which is what we said up here. So let's take a look at FC. So, but if we have an extra force here, so I have FC cos theta, and here I have FC sine theta. So if now I get some of the forces in the x direction to be 0, what's going to happen? I'm going to have minus FB plus FA plus FC cos theta. So I've got this extra force, so I actually don't really know what Fc is. So now if I take a look at some of the forces in the y direction to be 0, what do we have in the y direction? I have Fc sine theta, so which is 0. Therefore Fc has to equal 0 because it has no other y component. So therefore that is 0. And again we have Fa needs to equal Fb. So that's rule 2. And we have one more rule. And what do we have? This is rule 3. If I have a joint here, and I have my x and y axes, and here we have a force and another force. So if I just draw an axis in here, what's going to happen? So for this to be in equilibrium, and if I have my angles the same, okay, if this to be in equilibrium, what must happen? Both these members need to be 0. Let's take a closer look. So if I assume that, let's just draw it up here. That here I have, I'm going in this direction, okay? So if I break up this into its horizontal and vertical components, in the x direction, I'll be in equilibrium, I'll be okay, because this will cancel out with this force. But what happens here? The whole system is going to move up. So this is not in equilibrium. Okay? And then similarly, if I redraw that, here's my joint, and I have my forces, we've got the same angle, and if I'm going away from the joint, what happens? Again, my whole system, if I break up this into x and y, this is going to cancel with this, but what's going to happen here? My whole system is going to move down. And then there's one more scenario when we have one in tension and one in compression. So let's just draw that out quickly. This is actually written up in your notes. So here is my two members. So one is in compression and the other is in tension. And if I break this up into horizontal and vertical components, I'm going to go this way, and this one's going to go down, and that's going to go in that direction. So these two will cancel out, but my whole system is going to move in this direction. So again, we are not in equilibrium. So, to be in equilibrium, these forces must be zero force members. Otherwise, the system is going to move.